and we have Ola Jarvigen.
Sure, yes, Jarvigen.
Jarvigen, and Zach Smith, whose name I can remember easily because that's my son-in-law's name.
Oh, right on.
That's, yeah. Zach Smith, my daughter Stephanie, so Zach and Stephanie. You don't have a significant other named Stephanie, do you?
No.
That would be scary. But anyway, we go back a while now, I think just almost every year for the past 3, 4, maybe 5 years.
Yep.
They have come in and supported my classes, this class as well as Citizen Engineer. And wonderful company, does some great work. And I think you can see one of the projects that they've been involved with, which I think I've mentioned, not Mukilteo, but
Mukilteo, yeah.
it is Mukilteo, okay, Mukilteo. So anyway, without further ado, I will turn the floor over to Mr. Jarvigen and Mr. Smith.
Thank you for having us here today. We want this to be as interactive as possible, and so we're here to sort of present what we do as engineers in the HVAC consulting world. And so if you have questions, just intrigued, we would love to hear. Please don't hesitate to stop us, raise your hand. We really just want to make sure we give you a good understanding of what it is like to be a consulting engineer, and specifically talk about HVAC engineering and what that means. And so before we get into kind of those pieces, Zach and I are also going to play a little Jekyll and Hyde here. We're gonna give you a little doom and gloom, and then also give you the long-term answer or some more bright futures and some of the excitements that we share in the work that we do on a day-to-day basis when it comes to climate change and the impact that we as engineers and HVAC engineers have on energy use in our world. And so you'll see a little bit of that doom and gloom to begin with, and then hopefully we'll leave you with some excitement and some more purpose or enjoyment for the future. But before we get into that, let's tell a little bit about myself. My name is Ola Jarvigen. I went to UW, so go Dogs. Graduated in late 90s and been doing HVAC consulting now for, over 20 years. First job was actually manufacturing engineering. Did some manufacturing support for Corning Incorporated. They actually made optical fiber, and so I did support for that. Ended up losing my job within 6 months of graduating and didn't quite know what to do, and had moved to the East Coast, ended up traveling back west, and ended up just falling into the consulting world kind of randomly, and actually really started enjoying it. A lot of good reasons why I do what I do, and we'll get into that a little bit more later. But that's a little bit about me and who I am.
Hi, I'm Zach. I am from New York. I went to the University of Buffalo, go Bulls. Graduated in 2010, studied aerospace engineering, and Buffalo had like a dual degree aerospace mechanical because they're not so different until like the senior year. So my first job, despite being an aero, I graduated right in 2010, so that was kind of the financial crash, the other financial crash. And so didn't find a lot of aerospace work, and so my first job was a controls contractor for the railroad. So that was pretty interesting. Got to travel around. Railway yards are in a lot of cool cities, but not in the cool areas of those cities. So that was fun and not fun simultaneously. And then I played Ultimate Frisbee, and through a mutual friend found a job as a junior mechanical engineer at an HVAC firm in New York. And then back in 2015, moved out to the West Coast and have been here since. And Ola has been sort of my mentor the whole time I'm here. He's going to be the positive guy, and I, as the millennial, will be the doom and gloom.
All right, so today we'll go through introductions. We'll talk a little bit about our call to action and what we do, and then what's next for you as engineers, and sort of you transitioning out of college and going into the professional world and what that potentially looks like. Again, questions, feel free to stop us along the way. There will also be more time at the end to go through that. So As a HVAC consulting firm, we do a number of different things. Our main services are HVAC, plumbing and fire protection, and providing consulting support for commercial buildings. Along with that, we also get some sort of ancillary things that come in, sustainable design. The majority of the energy in the building is used by the HVAC system, right? And so we end up doing a lot of sustainable design stuff, energy audits, right? Energy modeling, and then also some other little things around that, like CFD and commissioning. But it all focuses in around buildings and those three central systems: air conditioning, plumbing, and then fire protection, right? So those are the three main services, but there's some other stuff that just fits along the outsides of that. Obviously this is me, Zach, and
I think this is me.
this is Mr. Smith, yes.
Okay. Going to a wedding this weekend, so wearing a mask just to be sure so I don't get my parents sick. Can you all hear me? Okay, cool. Wanted to talk a little bit about my own experience getting into the HVAC and sort of the paradigm shift that I had, especially when I moved to Seattle. So when I first started in New York, a lot of the projects that I worked on, I actually got to work on the old dormitory I was in when I was a freshman in college. And it was and they were finally, now that I had graduated, they were finally updating the laundry facility, and they were adding some more machines. So that was sort of as they added dryers, they needed to add dryer exhaust and more supply to compensate for it. So I was like, okay, cool, this is interesting, but not necessarily exciting. And then I got to work on New York has a program called BOCES, which is basically a trade school program for high school kids. So if they're not having success in sort of the traditional system, maybe they would find some more success or more joy, learning how to weld or learning how to be a beautician or any of those kind of things. So learning how to design those systems, that was slightly more interesting. And then I came to the West Coast and I got to work on the Mukilteo Ferry Terminal project. And that project, which we're sort of going to use as an example to sort of step through all of the things that we're talking about today, was more about climate change is happening. How can we create buildings that are beautiful and helpful to our society, but also are compensating for the fact that this thing exists and this thing is real. And so that building, the whole purpose of it was to be sort of light on the earth is what they called. And how that translates to engineer speak is we need it to be as net zero as possible. How can we create a 24-hour transportation system facility that used less or as much energy as it produced via solar panels? So that was sort of the lens that we looked at things. And a lot of the projects that I worked on, Ola he's a principal. He's sort of one of the owners of the company. Does a lot of the designs, kind of all over the place. I'm a sustainability project manager at my company, so I'm very sustainability focused. And so that's why I wanted to kind of lead with what we're sort of joking as the doom and gloom, and I promise you it gets positive, but kind of framing HVAC not necessarily in terms of like if you're an HVAC engineer, you're gonna design offices, you're gonna design air handling systems, which to me was the joke I always tell Ola was when I was in college, I didn't know what I wanted to do when I was a senior, but I knew I didn't want to do HVAC engineering. And now I'm an HVAC engineer. And there's nothing wrong with like if you look at this sort of thing, you're like, oh, this isn't too exciting. We're presenting a different way of looking at things. So fact of the matter, especially in the Pacific Northwest, the red dots that you see on this map are sort of indicate locations and indications of places that we're worried about with rising sea levels. And so there's seawalls being built to sort of compensate for these things, but as heat increases, ice melts elsewhere, and then sea levels rise as a result. Our over-reliance on fossil fuels over the course of our, especially the last 100 years, energy is only increasing in terms of our usage, and it's a non-recurring fuel source. It's going to run out eventually. And so we need to be proactive in our search for other things, and we're seeing more of a reliance on solar panel technology, thanks to that technology becoming more efficient over time. This on the top left is sort of a breakdown of the primary energy. Well, that's what it says: primary energy consumption in the United States, and you can see that commercial buildings and residential buildings. So on the right side of the screen, That's 40% of all of our energy consumption. So if we can really focus on making that as net zero, or we'll eventually talk about net positive, if we can make that as efficient as possible, or if we could reduce the amount of energy that we're using on the grid for that 40%, we can start building a society that's adding more, adding energy to the grid rather than taking energy away from the grid. And then sort of building towards the positivity, y'all are our ace in the hole. Gen Z tends to be more of a, not necessarily progressive in terms of a political standpoint, that may be the case, but progressive in terms of like, this is a problem, we're not dancing around it, let's fix it. Everyone else, millennials included, are like, what do we want to do? Y'all are like, screw it, let's do it. So y'all are going to be the solution to our problems. It sort of sucks that it's falling to you, and we'll be here for some of the ride, and then we'll get old and we'll get out of your way, and you'll fix it all for us. There's a lot of policy in place, whether it's the city of Seattle or Washington State or sort of global initiatives to try to move us towards more of a net zero and net positive structure. The Washington Clean Energy Act is looking to basically take our energy grid. So if you use electricity, you're not necessarily using clean electricity. You have to create that electricity somehow. So our source energy, if that's burning coal, for example, you might be using electricity, which is better than using natural gas from a sustainability standpoint. But if you created that electricity using coal, then it's kind of dirty. And so we're trying to make clean electricity. I can't tell you how we're doing that, but I can tell you that we're trying to do it. And then there's other initiatives as well. I believe there's the 2030 challenge. The Architects Institute is trying to get all of our buildings by 2030 to be
same buildings they were in the late 90s or something.
Yeah, I think it's like it's a progressive energy goal to get less and less energy intensive over time. And then basically, this is just a very pretty slide that says it kind of impacts us in a lot of different ways in terms of energy usage and having sustainability. Also, in addition to being lower energy use, there's initiatives to have more green in our spaces. So a lot of skyscrapers you'll see have green roofs. There's an initiative to have more green in our lives. So it's green from a less energy use perspective, and then it's literally green by having more green in our lives. And so these are just some of the things that are kind of coming down the pipeline. We wanted to provide you some real world examples of what these look like. So basically, energy codes are sort of the codes and the rule book that we have to follow when we're designing our buildings. And those energy codes are becoming more fully electric. So right now, I think in Washington State, in the city of Seattle, if you want to build an HVAC system for a commercial building, for the most part, it has to be electrically sourced. You can't, so whether that's like a refrigerant-based system or what, it can't have natural gas. There's some exceptions to that are going to be phased out in the next energy code.
The state of Washington just passed a law that requires all buildings in the state as of July 1st, 2023 to be all electric.
Yeah, so we're getting there, and you might be thinking that's really hard for the people that manufacture these units. How can they make them more and more efficient? They can. You buy a computer 10 years ago, you buy a computer today, in 2 years it's going to be incredibly poor in terms of its performance. People will figure it out. And there's grants and stuff to keep businesses going. We're not just kicking businesses to the ground. And the last thing that we wanted to point out was, or I guess two more things we wanted to point out here. So LEED and Living Building Challenge, there's sort of a LEED is sort of a incentive system for like high-rise buildings to create sustainable designs. So there's like a certain set of points that you can go for when you're trying to construct your building, and the more points you get, the higher your LEED rating, and the higher your LEED rating, the more like a high-rise apartment building can charge for rent. So there's sort of incentive structures to force developers to create better performing buildings, and that's a really good one. And the Living Building Challenge sort of takes that a step further. And basically, if you're going for a Living Building Challenge, you're basically creating a building that's net positive on the earth. So you are harvesting more energy than you will use. So you're actually adding energy back onto the grid. And then we wanted to provide one example of the private sector sort of doing this on their own. So the Microsoft's campus in Bellevue is looking to be net negative carbon, which is sort of the inverse of saying that they're going to be net positive in terms of their impact. And so they're taking a look at how their buildings are run and sort of how their whole logistical system is run in terms of like their delivery structure, how much gas they're using to transport, and they're trying to factor all of that in and make and reduce the amount of carbon that they're putting out there to a negligible level. Okay, that was a lot of information about that was sort of our context setting. We're going to talk a little bit more about what we physically do on a day-to-day basis. Before we get there, does anyone have any questions about what I just sort of sped through? All right, Ola is going to talk about what we do and make fun of me for this picture.
Well, before I get into that, I just briefly want to say too, policy is extremely important for us because a lot of times there is added cost to doing some of these things, right? And owners and first costs are extremely important to the clients we work in, as much as sustainability for some of them is also important. And so policy then gives us a roadmap and some requirements to push our industry to be better and not just use the sort of typical system of dollars and cents, right? Not to get into too much of the environmental policy stuff that there's another course for, but that has a huge impact on our industry and the things that we do day to day. And for me, being able to feel like I do something that's going to have an impact on the future is huge, right? I enjoy the purpose that I have as an engineer of inspiring and nurturing, my industry and my community. And so the ability to do that day to day is really what drives me. And I would, look inside yourself as you start to think about what you want to do with your career and find something that, has a little higher meaning, right? Because that's really where there's some good drive. That's when you can find something that really you will enjoy for the rest of your life. That's a really tough thing to find sometimes, and I feel extremely lucky to have found it at a young age. I went to college, I was not going to be an engineer when I started, ended up really enjoying physics, did the mechanical engineering thing, did some manufacturing support. That was fun and technical and joyful, and then ended up just through chance landing in this industry that I've now found this passion for and really, really changed my life. And it's great to be able to wake up in the morning and go to work with something where you actually feel like there's a drive there. So as you ponder your future, I would say, think about that and look for that. And if you don't find it, that's all right. You'll find it sooner or later, right? Sometimes by happy chance and sometimes not, right? So, but it is important. So enough of that. A day in the life of, and as an engineer, as a mechanical consulting engineer, I don't do a lot of things that I learned in college. We have software programs that do those things for us, right? We have a load calculation program that we enter in geometry and systems, and it runs our calculations for us. So then you might wonder, so why am I learning how to do those things? Well, it's important to know when those things are wrong, right? I still have to be able to look at the numbers and understand what those numbers mean. I have to be able to look at those numbers and say, wait a minute, this is wrong potentially. And as a principal and a mentor and a coach to young engineers, I have to be able to teach those things too, right? And so the idea really is to learn the fundamentals, right? What are the basic things behind the stuff that goes on a day-to-day that you need to know, so that when you then come and start relying on other things to do those things for you, you still have to know when it's right and wrong. You have to understand what those numbers mean. And so really it becomes more of that type of thing, where you're not necessarily sitting there cranking on a calculator or whatever, right? You're still, but you just need to know, right? I do basic algebra in my day-to-day life, but I don't do any calculus, right? Software does it for us. And so I think the real major difference there is that is one of the major differences. You won't really sit there and do that stuff, but you need to know it so that you can start to make decisions and understand what those things mean, right? So that is one of the differences going on there. And then as a consulting engineer, we represent our clients' interests, right? Client hires us to come in because we are experts in HVAC, fire protection, and plumbing engineering. We don't want to make decisions for our customers, right? We're really there to educate them so they can make the best decision for them, right? We meet with our clients, they tell us here's our project requirements. We want this, we want that, right? We want a building that's this big, we want these spaces in there, that sort of thing. And then we say, okay, great. Here are 3 different options of how you can approach HVAC for this building. And we say there's the pros and cons with this and this, right? So we go through, we have this decision-making process with our clients. But in the end, our clients are the ones that make decisions, right? That's the consultant portion of the things we do, right? We consult them so that they make decisions on what's best for them, right? And so there's a lot of interactions with people, right? We work on design teams that have sometimes 50 people, right? And so you really work in large teams. And so I think classwork, when you think about doing project teams with other folks together, that's really, really important stuff. And knowing how to work with individuals, and sometimes work with individuals you might not get along with, right? Zach and I get along, that's wonderful, right? We have a good relationships in and out of work. I don't have that perfect relationship with every single individual I work with, right? And so I still need to be able to work with them. Or maybe a client that's a little, I would perceive as difficult, right? I still have to understand how to connect with them, build that sort of relationship so that I really can consult with them, right? So a couple of really important pieces there is just teamwork. We'll get into that a little bit more as we proceed.
Yeah, I would say we've been talking a little bit back and forth about what advice, if we had a short list of advice that we would give all of you in terms of if you were looking to get into this, I think working on your communication skills is probably the most important thing. There are plenty of people in our office who are really, really solid or really, really impressive from a technical standpoint that sort of struggle from a communication perspective. So they have to level up those skills, and then there are some of us that are not good from the technical side but really strong communicators, and we have to level up on the technical side. If you feel like you're strong, you're in college right now, so you're heavily inundated with technical stuff. Really, really make sure you're practicing your communication skills. And a lot of I think for this project in particular, a lot of the times when we're hired, the person that we're interfacing with is not an engineer. So when you're consulting, it's not just about saying hey, I think the refrigerant system is better than this system. You have to sort of explain why, and explain in layperson terms in a way that is beneficial for them to understand, or beneficial for them to know, so that they can turn around and they can explain it to the people that are the decision makers. They may not have the final say, they may just be your point of interface. So you need to educate them in a way that makes sense, and we'll get to some more of the technical things that might be good tools for that, and also challenging tools, but really focus on the communication piece. So if you have friends that are I don't know, English majors or communication majors, and they're asking you a question about what you're doing, practice explaining what you're doing in a way that they could turn around and, I don't know, sell it to someone else. I don't know, think about that.
Yeah, this technical speak, our clients just look at us going, what did you just tell me? Right, speaking my terms. So yes, that is extremely important. Muckle Teal Ferry Terminal is a project that Zach and I worked together. We started it back in 2015. Very similar to what I said before. A client comes to us, or we are part of a larger team, and they say, right, we don't have a ferry terminal. If you remember, I don't know if you've used the ferry terminal from Muckle Teal to Whitby. There was no terminal as of a year ago, right? It was just a slip, real dangerous. Passengers had to walk off the slip where the cars were also driving. And so it's just not a good situation for the client. And so there's been a desire to put in a terminal for Muckle Teal for some time. So they sort of put together a quick program, they bought a site, and then they come to the design team and say, here you go, you have a site, we know we need a terminal, we know we need these kinds of spaces, put together a building for us, right? And another big part of it too has to do with the tribes, right? All of the ferry terminals are on land that was really tribal land, right? They lived there, that was their land until, I think we all know the history and don't want to get into that too much, but in order to sort of work with the tribes, that was the compromise that was made, is to make sure this facility was light on the earth. Right? That was really what the tribes asked ferries to do, was to create a project that was light and even gave back as much as possible. Right? And so that was information that the design team then received, and we took that and started to really put together, a project, right? So we're given a very sort of basic information, right? It's like waiting and relaxing space, right? An unused site, right? So these are all the things we're sort of given as a team, and then they say, great, now put together this building for us, right? And so going back here, what ends up happening, and this is not a good image, but the project ended up using the longhouse as its sort of form, right? So the architects created then a building that mirrored the longhouse that the tribes had. So now we're also creating a building that sits on a site that's tribal. It gives homage to the tribes, right? And we start to then brainstorm solutions, right? How can we take these project objectives and come up with a building? How do we go through these, right? So we do that through a number of different charrettes, they call it. Have you guys heard this term before? Charrette? It's not a term I knew until I started doing this either. Really what it is it's sort of a brainstorming session. It's getting people in a room that are involved with whatever the thing it is you're doing, and just throwing stuff on a whiteboard, right? Start communicating. What about this idea, that idea, right? So then you take all those little things and you start to take those project objectives and drive in a little bit more, right? And you start to develop and form ideas around some of these things, right? So now we get the longhouse, we get the light on the earth. And so what does light on the earth mean for Zach and I as HVAC engineers? Well, it means low energy, right? Efficient systems, solar cells that we can generate, rainwater harvesting, right? And you can start to see some of these things come to life here. This is a cross section of the building. This is a beautiful, marketing image. But we start to see some of those things we do, where we capture rainwater, right? We capture that water and we use it to flush toilets, right? So we're limiting the amount of water that we're using in the building, right? And then Zach and I will take that and say, okay, how do we design a rainwater system? Well, right, so then internally, now we start to do our engineering, our design work to then put together the components that we need to do so. Another thing we did is obviously daylighting, right? You can see that there are really tall glass, right? So we can limit the amount of light in the building, again, lowering energy use. We put in radiant heat. And in this case, radiant heat makes a lot of sense for a few reasons. I'm going to ask you questions, see if you guys can. What would be a reason why you might want to use radiant heat in a building potentially? Like, what is the benefit of doing a radiant? You have a concrete slab, you heat that slab up. What would that potentially do for you?
In addition to being really bougie and cool.
Yes, and sustainable. Well, what it allows you to do is think about standing outside in the sun. How do you feel? You feel warm, right? Even though the temperature next to you might not be so warm, right? So in a case like this, we can actually have a lower indoor temperature, which saves us some energy by heating up the slab, because you're going to feel warmer, right? And the reason we do that in this building is every time they load the ferry, they open up the doors sit open for 10 minutes, and you have this rush of cold air in the winter that comes in, and so that then air then needs to get heated up again, right? And so that allows us to have a lower temperature, which saves us energy by not having to constantly raise it an additional 5 degrees, right? And so this is one way that we can then take this information that the client gave us about being light on the earth, turn it into a design, and then say, great, now how do we save energy, right? We do that by putting radiant slab in, right? Lowering the indoor temperature, saving energy, right? So this is sort of the process that the design sort of tells us goes through. So radiant heat, we also ended up doing hydronic heat pumps. Have you studied the heat pump cycle yet? Right, so you understand the efficiency of the heat pump cycle, right? When we're burning gas, efficiency is less than 1. Heat pump cycle somewhere between 2 and 3. right? I mean, it can get even higher if you're doing some, heat recovery stuff. But right, so now we're starting to take advantage of the heat pump cycle because it saves us energy. In this case, it was interesting because the building wasn't going to do natural gas at first, right? That is a much cheaper system to put in than a heat pump system. What happened here is there was no natural gas on the site. In order to get natural gas to the site, we had to run 5,000 feet of gas in the ground. That has some significant cost to it. So we were able to show our client that we can offset that cost, offset the more expensive cost of the heat pump system by not putting in a gas line, right? So we were able to then consult our client and say, hey, here's some real data, cost impact that will meet your intent here without added cost, right? So these are the types of things that we do then, and put this data in front of our clients, give them the data they need to make decisions, right?
It would have been it would have been at least $250,000 for them to run the gas line.
Yep.
And that was, construction was going on pre and then during the pandemic, so those costs would have gone up.
Right. And the equipment was about $200,000 more expensive, right? And then the gas boiler is real cheap. The newer air to water, especially when we do air to water, it's not cheap stuff to buy. And we also have to think about defrost, right? How do you pull heat from the air when it's 20 degrees outside? That's tough, right? You start to freeze your coils, so now you have to put in more equipment to counteract that and things like that. So, these are the challenges that we face as we design things. Some other things outside of our building, pervious pavement. It's real important, because you have cars in this huge waiting, queuing area, right? There's oil and other things that drips down, and that all has to be controlled. And so you can put impervious pavement so it goes underground, and have treatment systems underground. This is outside of what Zach and I do. This is more of the civil site engineering stuff, but these are all sort of sustainable things that we did on this project. So pervious pavement, stormwater infiltration, rather than just allowing that to just run off into the ground. And then lastly, the project ended up putting PV panels on the roof in order to generate energy on site, which has become way more prevalent in our area, right? Cost of PV panels have come down on a kilowatt basis. Energy costs are starting to creep up, right? So the payback calculations that we see for these systems are getting better and better every day. They're not as good as we would like them, or our clients would like for them to be. That's where policy comes into play, right? Policy can then drive decisions and in a certain way force the hand of clients, because if we don't do this, we will have a problem, right? We're starting to see that problem today. And I think for me, the bigger problem I have with this is it might not impact me, right? The global climate change thing for us here in the state of Washington, specifically Puget Sound, is pretty minimal, right? We might get a little warmer in the summer and things like that, so the impact for us isn't here, but think about the impact of somebody that's in Bangladesh, right? Most of their country's underwater, they're getting more storms, right? And so the things that I do here is going to impact other people who might not have a choice in what I do, right? And so let's be good stewards of the world. Let's do what we can as engineers to help everybody create a world that's better. And then
We'll talk about that.
we'll talk about passive ventilation here in a little bit. Super interesting. Zach did some great stuff. We'll get into that in just a little bit. And I'm going to actually hand it over to Zach again.
Yeah, so wanted to break down, some of the tools that we use. Ola sort of mentioned at the beginning when he was talking about the softwares that we use, so we don't have to do a lot of like you don't sit down with a piece of paper and start like writing out capacity equations if you got into heat capacity. We have programs that are basically just like better user interfaces of like an Excel spreadsheet that sort of do our load calculations for us. How much heating and how much cooling do we need to add to our building to compensate for the coldest winter day and the warmest summer day? That same computer program has a way to input the efficiency, the type of equipment that we're using, how we sort of lay out our equipment, the efficiency of the equipment, and a variety of other things like how much lighting power we're using, how often people are in the building, so like an office building versus like a 24-hour ferry terminal. All these things sort of come together, and we're able to determine the amount of energy that we use on a day, month, yearly basis. And so we're able to put together studies this is a study for an architect that can inform design decisions. So just walking you through what you're looking at here. The y-axis is how much energy that we're using. It's in kilowatt hours. And then the x-axis is the percentage of the building that's called glazing. So glazing is basically glass area. Architects call it glazing or fenestration. Although all this means the same thing, but basically how much energy are we using if we go 40%, which is the maximum allowable that the city of Seattle allows you to do is 40%, versus if we had a building that had zero glass, which would never happen. But instead of sitting down in a room and saying, hey, architect, you should have less glass because it saves us energy, instead we could put together a chart that shows, hey, it goes down as you use less glass. It's a visual, it helps them understand that better. And they get it, but they don't want to use less glass, so you have to sort of steer them in the direction. You have to give them the information that allows them to make the best design decision for them, because they're balancing interests themselves. Yeah, and so you'll basically see that for the most part, the orange, and I apologize if anyone's colorblind, but if we've run into this a couple of times, so we're working on how to be better at that. The orange sort of decreases slightly as you go from 40 to 0%, and then the yellow is our cooling, that decreases as well. And it doesn't look like a lot, but when you're designing a net zero or a net positive building, anything that you can decrease is good. Once we finish our designs, there's like other stuff. I heard you talking about Honeywell. There's like controls analytics that you can do to sort of like help. There's the control structure of HVAC is even getting into like artificial intelligence and stuff like that. We can't talk about that because we don't know about that. We're sort of dumb, but sorry, dude. And but there's like the design, and then there's how the design is used. Does your significant other leave the TV on like my significant other does when she's not even watching it? All these things sort of matter. Okay, we talked about passive ventilation, and I'm going to share a little bit about my aerospace engineering background. So what you're looking at is an image from a piece of software that uses computational fluid dynamics. Computational fluid, anyone take CFD? Probably not. Good, don't take it. It's crazy. You have your velocity, let's just stick with velocity. You have your velocity equations in your x direction, y direction, and z direction. Computational fluid dynamics sort of takes the sort of differential equations related to those three different directions in velocity, and sort of gives you a map of how your specific building in this example operates based on a variety of conditions, based on a set of initial conditions. So we're able to open up weather information for Mukilteo, Washington, and we know for most of the year sort of like what the direction of the wind is, how fast the wind is going, etc. And we're able to determine if we opened up a section of our building, let's say if certain windows were able to be opened, how would air flow in our space? And so there was a mandate for this project that the main waiting area that people sit in, that area could not have air conditioning. So in addition to us trying to reduce energy as much as possible, that was just a specific mandate from the state of Washington that area does not have air conditioning. So during the summer, when you have that full glass wall that we were showing you a picture of, it's gonna get warm in there. Our heated floor is off during the summer, but still it's going to get pretty warm, so how do we cool it? And so we do this thing called passive ventilation. So we did a variety of studies where we investigated if we opened a set of windows on the left side of the image and on the right side of the image, what would the airflow pattern look like? And so we looked at sort of like how many windows were open, what height, it's a full height wall of glass. So like each of those sections could be opened or closed. And so we looked at that. And so what you're seeing in this image is it might be hard to see, but there are arrows in this image, and then obviously there are colors. Color represents different speeds, and then arrows represent direction. And so we're able to kind of do this until it makes sense to us, and then go to our client and say, here's what we think, and then sort of do a comparison of, we basically explain what color means. So blue is fastest moving air, because blue is going to make us feel cool, and red is air that's not moving at all. And we can say, here's design A, here's design B, which one makes sense to you?
So when you guys like do a CFD of this, or any kind of design choices to help consult, do you ever have to, because this is like software, do you ever have to like do tests or try and validate that before they start building? Are you guys able to?
We not in this case, right? This is we live mostly in theory, right? And part of it is because the client, we're not cooling, so this is just added benefit with limited cost. Now we also do a lot of work for Boeing and we do paint hanger design, where airflow around the plane is extremely important. In those cases, we actually test it afterwards. They go in and they put dye or sort of smoke generators, right? So once the project's built, before it opens, they put in a smoke generator and you observe how the air is then flowing around the plane, and we can check that against our models, right? So some cases, yes, some cases, no.
And this sort of speaks to what Ola was saying before about understanding the background of things, because this is a program, garbage in, garbage out kind of idea. So if you run, I ran this simulation a handful of times to make sure it was operating the way that made sense to me given my background, and sort of intuitively speaking. And so if you sort of shared the first run, it probably wouldn't make sense. And then one of the things that we've learned through doing this with Boeing and then through doing this with public agencies is anything that you show someone, they're going to run with. So you have to be like, actually, this image used to be, the color scheme was inverted. The default in the program is that red is the faster moving air. And so they saw the same image, but instead of red, it was blue. It was sort of like the color scheme was flipped. And they're like, oh, we don't want red, that's hot. And I was like, no, red just means fast. And so I was like, okay, I'm just gonna go home, I'm gonna reprint this image, and it's blue now. It's the same thing, but blue means fast. And so it's just like learning that, like, I guess impact versus intent in that situation, that anything you share is gonna be taken. And so we got sort of this, like, you get like a little bit of a circular pattern, head height is kind of like right here. And then there's sort of this whole, Ola was talking about it with the radiant floor, but there's sort of like a bunch of codes and sort of like white papers, I guess, about like how people perceive being warm versus like if they're actually warm or cool. It's not super interesting, but it's basically there are some guidelines on how to design for the perception of feeling cool.
Imagine standing outside in the wind.
Yeah.
Same thing, right? You feel cold when the wind blows across you.
On a hot summer day, but it's still hot outside.
But it's also uncomfortable if it's too fast, right?
Right.
So we want to make sure we get enough induction of air movement without it being a wind tunnel, right? So there's this sort of balance there about creating a sense of feeling comfortable, right? And not going too far and too below. So, just interesting, dynamics to work within.
And now there's a lot of clients that are asking us for this capability to understand how airflow moves in their building from a sort of a pandemic-related perspective. How does air move? If we space people out, how does that go? And so we're being asked to kind of view things in that regard also.
We actually model our own office to see where people should sit.
Yeah.
Right? If you put two people next to each other and the air's flowing this way, the person over here is maybe not so good, right? So how can you distribute people within the office to limit the spread of someone's airborne particles, right? Interesting.
Yeah. Sort of other things that we do, we might be asked to evaluate a variety of different systems. They might want to, like Ola was saying, the different systems that we use at Mukilteo, they might ask us, like, someone might have an engineering background and say, like, I really want this system. Or we might just, generally we usually present at sort of like earlier design levels, we might say, here's option A, B, and C. Instead of walking them through the technical details, we might say, we might talk to them and say, like, okay, what are like 10 things that are important to you? And they might say, first costs, how much energy it uses, how much it's going to cost over the entire life cycle of the product and of the building, how easy is it to maintain, all of these things, you know, how likely is it to fail, how excited are we about the idea of using this piece of equipment. And so we'll sit with them and say, we might have hard data for some, and we might have opinions about some of the other categories, and we'll say, let's rank them. And we go and we rank them and we ask them what's the most important, so we give that sort of a weight. And so this table is basically a weighted average score. Or it's not a weighted average, it's a weighted sum. And so we get to the end and we say, hey, this one has the highest score. Does anyone have any, do we want to, and then you might have like an iterative conversation about that. But it's sort of a really easy way of sitting people down instead of saying like, here's data, make a decision. It's, what do you think? And then, okay, based on what you think, it sounds like we're going in this direction. Does that sound good to you? So it's just another way of sort of presenting information to them. And then for any of you who are doing CAD courses, what we do is we create computer-aided drawings, we create blueprints for the construction of the building. In comparison to like architectural or structural, theirs are like very, very dimensionally important. Ours are more sort of like basis, like this is sort of what it should look like for the most part. We might say like, this has to go here and give that a specific dimension, but for the most part, we're basically saying, put this kind of in this spot, it needs to be able to do this. So we'll this is a floor plan that you're looking at, and then we'll have other drawings that say like, if you want to hook up, this is like a diffuser right here, if you want to hook this up, this is how you connect to it. And if you want to, you know, from a controls perspective, we want, you know, when the piece of equipment starts, we want to make sure this other piece of equipment starts, and we sort of give them the baseline control logic, and then they program it. Is this you? No, I got two more. So Ola sort of alluded to the fact that oftentimes we have very large design teams. Mukilteo, I think there were around 15 to 20 designers working on it at all times. And then there were the people that we interface with, and then the people that those people reported to. There was another project that we worked on that was going for net positive energy usage. That was called the Jameson Project, and that had about, we would sit in these meetings, these charrette meetings, with like 50 or 60 people, which you would think not a lot gets done, and you'd be right. And then the last thing, sort of wanted to talk about the progression of work and the progression of technology. And so, you know, back in the day of the dinosaur when Ola was in school, they wrote everything down with pencil. And then my generation started using Microsoft Word, and now you use cloud, you know, you use the Google Cloud to kind of share work live. Similarly with computer-aided design as sort of as a analogy, everyone used to, they had these things called Mylar sheets. They would draw with, not just pencil, but they would draw on it. And then the architect would go first, and then they would take the physical drawings and they would hand it to the structural engineer and say, like, okay, now you go. And then structural would hand it to mechanical, now you go. And so this would take like, every design is iterative. There's usually like 3 or 4 submittals in a project design. Now imagine like physically bringing the drawings and like, imagine if you mess up and you have to erase it. Super expensive and super inefficient. So we have, who's done CAD? Who's done like CAD courses like AutoCAD? Great. So now, you know, we started using AutoCAD, and now we do Revit. Anyone know Revit? For the most part, anyone know SolidWorks? Revit is like take CAD and make it 3D. Add like an elevation to it. And now we have this like 3D modeling software, and now they're taking it a step further where it's sort of live sharing of 3D modeling. So you're connected on a cloud server, and if Ola is the architect and I'm the engineer, and he decides to sort of change the position of an office, or if the structural engineer is like, hey, the beam needs to be located here, actually needs to be this size. We could see those design issues during design, or those construction issues during design, and then kind of catch the bigger ones. What's that?
So like, as consultants, what's your level of involvement with the design process? Because I saw like the drawing you had, but like how detailed do you guys get? Is it more just like, oh, this is a general kind of sense, and then the designers and the architects do the detail?
So we are designers.
Okay.
Yeah, this is like for these spaces, this is the finished product of this space.
Okay.
that we're talking about. Just wanted to point out that there were no dimensions on it for a specific reason, but this is a pretty detailed version of what you would go, and there'd be other drawings that would sort of add to this that provide additional information. But we sort of go from like a conceptual to a detailed level design, and this is kind of the final product. There are our counterparts on the construction team that sort of oftentimes take our 3D model, and they say, okay, we see what you were doing there. That can't physically be built, so we're gonna do it this way.
Yeah.
And they might say like, hey, is that cool with you? And usually we're like, yeah.
They're probably a different level of detail than we do. Right? They take it down to the nth degree about how tall is the duct gonna be exactly where it's put in. We put this support exactly right here. What we do is to show a long duct run and then give them some parameters, performance, right, specifications that they have to follow, and they do the details. So we design it, they put it together. And I think as engineers, we're more systems engineers, right? Where we take components and put them together to create a system, right? We don't design and put together the heat pump, right? We tell a contractor to go buy a heat pump, to go buy a pump, to go buy this, and then tell them how to put all those pieces together to create the system that does what we want it to do.
So they don't already have like a building design, and they want to say like, oh, put these equipment here. It's like, this is our constraints, and you guys design around.
Yeah, or we together with the architect, we're given the program, the architect starts to put together the building, and then we say, well, we need a mechanical room that's this big. We need this much space in the ceiling.
It's iterative in that way.
Which we're gonna get into.
Yeah.
Right, where we spend a lot of, I don't know if you finished.
Yeah, I think we're running low on time, so we might speed
Sounds
through
good, I'll
these.
speed it up. So really, I mean, we've talked a lot about sort of high level stuff, right? Zach started to get into more of detail, right? Where the iterative process is to do the high level stuff, and then you start to spin in and get closer into more and more detail as we progress, right? We pick a system, then we start to pick equipment, then we start to figure out how those pieces get tied together, right? And then we start to put together the diffusers and the individual things of each group, right? So that's the iterative process where you start high level outside and you slowly go in until you get to that level of detail. We talked about this one. I mean, it really is important, right? Last thing we end up doing on a project typically is just involved in construction, right? Contractors build stuff, but they don't want to take any responsibility. And that's not on them necessarily. They're just not engineers, right? And so we are still involved in that construction process in case something has to change, right? If they want to move something, they come to us and say, hey, is this going to work? We look at our system, we say yes. Or we say, you know what, how about this instead, right? So we're still involved in the construction, which is also another really, really fun part of what we do, because we spend so much time in this theoretical world and a model, and you actually see something being built. Right? My kids, I think every time I drive by a building and I say, hey, I worked on that job, they're just like, ugh, right? They're like, all right, yeah, I heard that one. But that's super exciting for me, right? That's something that I created to a certain point that I'm proud of. Right? So there's something really joyous in sort of seeing the finished product at the end, right? Yeah, right? Enjoying the final product. Another thing just for us, right? I mean, we're in the community. We're a mission-driven organization, and being involved in that community is important for us. So this is a picture of the block project where we're doing. It's an initiative to put a little single home on people's backyards to provide housing for folks that might need it, right? And so we're in the built environment, something we feel as an organization we should be doing to support the world around us.
And it's grid disconnected, so it's net zero.
Yep.
Net zero energy, net zero water.
It's got PV on the roof, it's got a little rainwater harvesting drain, right, those kinds of stuff. Here's a couple of different types of projects. We talk a lot about Mukilteo. Here's 3 other examples. The Union Gap is a civic, city hall type building for the city of Union Gap in eastern Washington, right? Sort of an office building. Salmon Creek wastewater treatment plant. Now we're providing building support for our wastewater treatment plant where we work with an engineer that's designing the treatment portion of the project, and then we provide the building infrastructure they need. And then over here on the right, that is, this is the Odessa Brown Children's Clinic, right? So this is part of Seattle Children's. It's a community clinic down south where patients come and get sort of community type care, some, primary care, some eating and just a community type facility for Seattle children. So a couple of different types of project types that we do. The majority of our work as a company started with Boeing. Now we're sort of entering more into, but a lot of it is the public realm, right? So ferry terminals, city halls, right? Educational facilities. We do work at Evergreen and Western, right? So just different types of projects, which is another wonderful thing about what we do is there is not one end the same, right? Every single day, every single project is different. Even if I were to take, I have one project I work on where we're doing the same thing in different locations, right? You might think that gets repetitive, but each location is different, right? I have an existing building I'm going into. Yes, I'm putting a program that's similar and similar systems, still a different variable, and even if it's a different project team or different client, right? So there's so many variables that change. There's nothing one and the same. So the variety that we do is wonderful. Does not get monotonous, right? And so it's constantly new, challenging, right? Which as an engineer is fun, right? You're solving problems, which is wonderful. So transitioning, I think, it's going to be different. You're going to stop dealing in theory. You're going to enter in and deal more in the real world. But it's fun, it's exciting. I'd say, get your resume going. I will encourage you to take the EIT before you leave, even if you don't get your PE later in life, which in some professions you don't really need to. In ours, you should, right? Well, Zach and I didn't, and that's been a challenge for us in our careers somewhat, and doing it 10 years later is harder, right? I rely on this program. Like, I don't remember some of the formulas, right? It's like, it's really hard to do later in your life. So take the EIT.
Yeah,
I encourage you to do
the
that.
Fundamentals of Engineering exam.
Yeah,
If you haven't
yes.
thought about taking it, I just took it 6 months ago. I haven't looked at similar triangles for 10 years. It's you're really in a good spot to take it with minimal studying and pass it now. I would do that.
Yes.
I would do that like either before you graduate or right after you graduate. Well, you're pretty close to graduating, so consider doing it like in the next 3 to 4 months. And then this is an example of a resume, and then also LinkedIn it's good for a lot of things, and building a network is really important to helping you find not only your first job, but your first job that you want, first job that you're going to feel comfortable in. The more people that you know in the field, the more people you can ask about certain situations and make sure that the company that you go to is the fit that you're looking for.
And network, right? I mean, part of the reason we're here is we want to support the community that we're in and the industry that we're in. Start building relationships with folks, right? If you want to go on LinkedIn and become, I'm part of my network, I'm happy to do that. If you want to ask questions later, Mr. Collins, I can give you a business card, right? We're here, we want to support you and provide, answers and questions and all those kinds of things, right? So I think that's another thing is really start to network and look at those opportunities that are out there, right? As you start to think about the transition to being a professional.
And then take a look at any of the advice that you could find online about interview prep. It's all about being comfortable in a conversation, and those skills that you would work on if you practice for interviews are directly translatable to your day-to-day life as an engineer, no matter what you're doing. So consider investing some time in that. It's really great to practice that with others. Just be comfortable having a conversation. That's what we have. Sorry, we sped through the last third of this because we realized we were kind of droning on. But does anyone have any questions? Yes?
Yeah, how much, field work is involved? You mentioned that a lot of times you guys work with the construction workers to make sure that the plan is going according to plan. Is that usually the original designer that's working with the construction?
It's going to sort of depend on the company that you go to. My first job, you were sort of you got assigned a project, and you saw that cradle to grave oftentimes. Our structure at our company is to sort of make sure that no one is overburdened or underburdened. So oftentimes, OLA typically takes on a lot of work. We sort of look at we're going to jump on our company meeting on the way home, and we'll know hey, OLA, you have 60 hours tasked to you. You're not going to work 60 hours this week. Who can you share tasks with? And so sometimes, I might not have seen a project, but I might go on a field visit and be like, okay, this sort of matches. I could sort of answer this question. And then in a broad sense, oftentimes field work is in the beginning of a project if we need to sort of look at how a building is, the existing building structure and how things are laid out. and then oftentimes during the construction process. So depending on how many projects you have in sort of their state, it could be a semi-frequent part of your day or a rather infrequent part. And there's the last part where we have certain people that do what's called commissioning, which is basically what you were referring to sort of with the CFD stuff, but commissioning is like active testing of our systems and the control of those systems. So Ben, this gentleman over here, is one of the other principals of our company, and he's sort of our lead commissioning guy. So he's very frequently going in the field and making sure things are working as designed. So if you were a commissioning agent, that could be like a almost daily part of your life.
It really, that's where most of the learning that we find. It's really easy to live in a theoretical world, right? Everything's perfect. It works great. When you get out and actually put something to use, is really when you start to figure out what works and what doesn't, right? So it's really when you get a lot of the learning, right? And contractors will tell you how dumb you are because you did this and the other thing, right? And there's a lot of truth to that because they know how to build buildings, right? We can put these models together, it's all perfect, and when they hand it and start building it, that's not how it comes out, right? So there is a ton of learning, hands-on, just going out to the field, seeing something, looking at it, and sort of how does it really get put together in a real world, right? Theoretics is wonderful and great, but there's not always that one-to-one transition to the real world, right? So you get a lot of learning in field work, and so we definitely encourage our young engineers to get out there and learn, and with the support of a mentor as well, right? You don't want to just throw people on to the real world all the time, right? Support along the way is important.
I wanted to ask, what are maybe some of the specific benefits and challenges of working in the consulting side of engineering versus maybe more standard?
I can go first.
Go for it, yeah.
I would say, you said advantages and disadvantages, right?
Yeah.
So I would say advantages of consulting. So you could work at Boeing doing HVAC engineering, and you might get one project that you sort of sit with for a really long time, but it's your project, and that's really cool and really empowering. Or the same thing is true of the site engineers that work here at this school. They might have one or two projects. I think one of the benefits of consulting is that I'm on 5 or 6 projects right now. So I get to kind of put my head into, depending on the time of the year and which project is sort of on and which ones are off, I get to wrap my head around different things. So I'm working on transportation work, I'm working on healthcare work, I'm doing some Boeing work, so I get to kind of jump around and do those things. And then I would say a disadvantage is it can be incredibly frustrating. You go, you do all of this work, and you say I really think it's in your best interest to do this, and sometimes they say, okay, we're gonna do it. We're gonna do this other thing then. And I'm from New York, and I'm a very aggressive person by nature, and that was hard for me to adjust to. And so that's something to consider. Being if you're that engineer at Boeing, you might have more decision-making power, and that might be more interesting for you.
So yeah, I would echo that. I think the variety of the work that you see as a consulting engineer is different than a lot of the other industries where you might, if you do manufacturing, you're working for, some air-to-water heat pump manufacturer. You learn that's what you do. You get really into the details for whatever that is, right? We apply that to multiple situations, right? So the variety of work is fun. I enjoy that. I enjoy being challenged in different ways. Not that that's not challenging as well, but it's really that idea that nothing is one and the same, right? Everything's different. And then yes, you do end up in situations where you're being told what to do, right? As much as you want to consult them, you gotta just do what they ask, right?
What were, you said initially you were like, I'm not gonna do, HVAC
Yeah.
or whatever. What were some of the things you found that were different than what you thought? And how do you compare your career to maybe your other mechanical engineering?
From my class?
Yeah.
Sure. So I would say the reason why I wanted to bring that up, because when I was in your shoes in college, I thought HVAC was a really boring topic. Sorry. So I wasn't motivated by it. I was taking aerospace courses. My favorite class was propulsion. I was super into it, and that was what I thought I wanted to do. I thought I wanted to work for Boeing. And I think when I was at my first job, the first 2 years I was working in HVAC when I was in New York, a lot of that assumption felt true. I was like, I felt like it wasn't very interesting. And then I came here, and sort of the paradigm shift, I think part of it was the sort of company that I work for that's like, you know, very communicative. It's sort of the opposite. Some people fit the engineering stereotype, but a lot of us are a lot more outgoing in nature, and it makes things a lot more fun for me because I'm extroverted. But I think the switch to considering things from a sustainability perspective, that was such a challenge to me in my mind, and it became less about, you know, I think I walk into a room like this, and most times I look up and I see how things are done, and there's the I find that more interesting now. But I think most of my brain is like, how do I make these net zero buildings? How do I help design infrastructure that's going to be long lasting? And that's sort of that was the switch that flipped for me. A lot of my classmates are in manufacturing engineering. One works for a company called Moog, which is in New York. They do a lot of like control stuff that goes to you know, a variety of transportation or military. Some of the guys work at Rockwell Collins, which is like a helicopter company. And based on my experience working with Boeing, you get very kind of, I'm not trying to turn anyone off to the idea of Boeing, but if you're a Boeing engineer working not in the HVAC side, you're working on like a very, very small component. You're not working on an airplane, you might be working on like a seatbelt. And that's just the reality of it. Unless you're trying to get a double PhD, then you do whatever you want. So it's sort of just like, I think maybe one more thing I would sort of add to it is sort of the latitude we get to sort of like express ourselves and find things that are interesting. HVAC seems like pretty basic, but there's a lot to it, and there's a lot that you can find yourself kind of meddling in.
Yeah, wineries, right?
Oh yeah,
getting
wineries.
into breweries and distilleries, right? There's a lot of engineering that gets into the behind parts of putting that together, right? So it's just interesting from a lot of levels where you start to, you know, expand it outside of just air conditioning and plumbing, right? It's still within that realm. So now we're putting together, you know, being part of a wine processing, right? And putting those pieces together. Real interesting stuff, and just a complete variety of things we do on all different projects.
And cannabis too, if you swing that way.
Yes. So wonderful questions.
Any other questions? Well, thank you. It's a wonderful
Awesome.
presentation. You guys covered a lot of ground.
Hopefully not too much too fast.
Yeah.
Sorry.
Yeah.
Well, thank you for having us. We really appreciate it. Thank you.